we are going to start the lecture on nanotechnology in chemical engineering. So, today we will discuss about application of nanotechnology or nanomaterials in heat transfer operations. So, heat transfer, that is very important unit operations for chemical engineering process. So, here using nanomaterials, that is help in heat transfer operations. So, how that is affect the heat transfer operations. So, that will convective heat transfer, that will discuss. So, here in today's we will discuss basically heat transfer fluids and its properties. So, usually for heat transfer operations, a heat transfer medium, so that will carry the heat from the source to transfer to another place where temperature is low. By that way heat transfer operations will take place. So, here a medium that we can use, that is called heat transfer fluids. So, heat transfer fluids is very important, and then once with the base fluids we add some nanomaterials. So, we said that nanofluid plays significant roles in mass transfer operations. Similarly, additions of nanomaterials in base fluid to prepare nanofluids, so its property will change. So, that the property means thermal conductivity or heat transfer coefficients that may enhance. So, as a result rate of heat transfer that will increase. So, preparations of nanofluids, one step, two steps methods, that already have discussed, that also again slightly we will discuss, and then synthesis of nanofluids and few examples we will discuss. Okay. So, heat transfer fluid, basically I said that heat transfer fluid that is used as intermediate media to transfer thermal energy from one heat source to the various heat sinks or cold streams, so where heat is required. So, commonly the heat transfer fluids that we use, waters, and it has a high heat capacity and low viscosity. Therefore, most commonly we use water as a heat transfer medium. So, it has some limitations, since waters for a place when temperature is 100 degrees centigrade, 110 degrees centigrade, within that low temperature range. So, there we can use these waters, but when temperature we have to use 200, 300 degrees centigrade. So, there we have to use some synthetic soils as a heat transfer fluids. So, that is stable at high temperatures, then waters, so that we have to use. But apart from, means if we go beyond 400 degrees centigrade, that particular synthetic oils we cannot use for heat transfer medium. So, then we have to go for molten salt mixtures we can use, that is stable at high temperatures, and that stability is higher than water or synthetic oils that we can use. Okay, so that is the property actually heat transfer fluids that we can use. So, even for extremely high temperatures, when applications is more than 550 degrees centigrade, so in that case we can use CO2 or helium. So, heat transfer operations, and there's we can, and these two gases means CO2 and helium we can use when pressure is, operations pressure is extremely high, 150 bars. Okay, so and these heat transfer fluids can be used for different applications. So, the property of the heat transfer fluid is very important. So, it must have high thermal conductivity, high specific heat, low viscosity, and chemically or thermally stable that fluid must be, and non-corrosive and non-toxic and non-flammable. So, these are the properties of heat transfer fluids that we have to use depending upon the cost, viscosity and other properties. So, we can select or choose a particular fluids for heat transfer operations. So, here's different heat transfer fluids that I am showing here for thermals, Diatherms give molten salts that can be used. So, here's means working fluids already we have discussed. So, therminols, diatherms give high tech XH helium CO2. So, depending, these are the up to 400 degrees centigrade we can use, and these we can use up to 550 degrees centigrade for heat transfer operations. If we go beyond that, so then CO2 or heliums we can use. So, these are non-toxic, non-flammable, non-corrosives. Okay. So, and also this particulars means fluids, whatever the property that is important specified, and I said the thermal conductivity, that is very important. So, these fluids at means low temperatures thermal conductivity, let us say for helium is this. So, when temperature is increased, thermal conductivity also will increase. Similarly, if we go high temperature, the thermal conductivity also that particular fluids will increase. So here for waters, ethylene glycols or therminols, different type of thermal fluids is there. So thermal conductivity value is also depending upon that fluids we have. So now we are going to discuss about nanofluids. Nanofluids already we have discussed. So there's we have to use nanomaterials, so that may be range 1 to 100 nanometers. Within that range, that would be dispersed uniformly in a base fluids, that may be waters, ethylene glycols or any other solvents that is suitable for that particular operations, heat transfer operations we can use, and that nanofluids acts as a media to transfer heat from one particular point to the another particular points. Okay. So here commonly nanoparticles, I said different type of metals, metal oxides, these carbides or any carbon based materials also we can use the nanomaterials for to prepare the nanofluids, and common base fluids may be waters, EG or mineral oils we can take. So these are the various applications, so where we can use. And so challenge for using of nanofluids for heat transfer operations is agglomerations or settled within, means if we keep it for longer period of time, so there is a possibility of settled down or agglomerations of the nanoparticles in that nanofluid. So that is the challenge, and also we have to choose that fluids having a low viscosity that easily we can transfer from one point to the another point. As a result, pumping cost will down. But if that we have chosen some fluids having high viscosity, that would increase the pumping cost or pumping powers. Also the nanoparticle synthesis means that is very expensive, therefore overall the nanofluids that we prepare, that will also increase the cost. So that also we have to keep in mind. So when we will prepare a nanoparticle, and that particular nanoparticles we are going to use to prepare say nanofluids. So here base fluids already have discussed, and different type of metals, metal oxide, carbon based nanomaterials we can prepare for preparation of the nanofluids. So here nanoparticles, and this is the base fluids, so we can use for the preparation of nanofluids. So here two different methods already you have discussed, means nanofluid property, that is also important. So actually the nanoparticles have 1000 times greater thermal conductivity than conventional water. So normal water we can use, and by additions of nanomaterials and prepares in nanofluids that having 1000 times greater thermal conductivity than water. So that is the advantage of using nanomaterials for heat transfer operations. So here base fluids properties means any fluids we cannot use when we prepare say nanofluids. So operational temperature is important. So when operational temperature is high, so then waters we cannot use as a base fluids. So then some other fluids we have to use where it can work high temperatures. So oil based nanofluids that having high thermal stability, that we can use for high temperature also. Okay, so different type of fluids having different stability and thermal conductivity value also, and here you can see different materials we are using, and it has different thermal conductivity value. So here's different metals, it is having that much of thermal conductivity, and here you can see graphenes or carbon based nanomaterials having thermal conductivity very high, even heat capacity also extremely high in this type of carbon based nanomaterials. So here means silicons oils also we can use, so that is having high means thermal stability. So now the properties of the nanofluids, so we are using base fluids and nanomaterials to prepare the nanofluids. So here we can prepare the nanomaterials, already have discussed one step methods, two step methods. So here's in one step methods, Veros and Sons, these methods are used, and two step methods is also there. So two step method is much more better than so one step method. So but in one step method, so here's advantage is that here low nanoparticle agglomerations improving nanofluid stability. And okay, so here technique used PVD, physical vapor depositions, the nanoparticles produced vapor depositions, and vacuum evaporations onto running oil substrates. So metal vapor that will be condensed into the nanoparticles, and which are then disperse directly into the low vapor pressure fluids. So, in this various methods and modified various methods, there's metals vapor that is condensed into nanoparticles that directly disperse into the base fluids. So, here's direct evaporation condensations we can do, or we can prepare nanomaterials and then we can disperse into that base fluid. So, here is various methods is there. So, here details methods is given. So, extremely fine nanoparticles we can produce and that we can disperse in that particular oils or base fluids we have taken. So, here this is the reservoir for oil and here rotating disc is there and here crucible is there. In that crucibles we can maintain high temperatures and then vapor of that particular metal or metal oxides will forms or nanoparticles will form, that will be come here and here cold surface is there, or where base plates will be through this rotating disc that will be mixed up and we can get oil with superfine particles, we can get it here. This is the base plates actually nanofluid preparation methods, or submerged arc nanoparticle synthesis methods, that also we can use. So, this is also similar like that. So, here electrode is there and some fluids is there, here high temperature you have to maintain. So, means by that metals rod that you have to take here, so these metal rods that would be heated by an electric arc and there will maintain 600 to 6000 to 1200 degrees centigrade and metals will be melts and vaporized, that would be means then mixed with that liquid is theirs and that's it would forms a nanofluids. So, this is one step methods and now we are going to discuss two step methods. So, in two step method also we discuss. So, we can prepare some nanomaterials and nano particles separately and base fluids we have both, we can mix them up by stirring, so we can get nanofluids. Okay, so here nanomaterials may be anything, so that may be metal or metal oxides we can use, and base fluids that may be waters, deionized water or ethylene glycols we can use. So, each steps method, so means one step method or two steps method, some advantages are there, some disadvantages there one step method. In two step methods also large scale productions, that is the advantage in this methods, and we can prepare, means this method is cost effective methods. In this methods, actually two step method, drying of particles is required, agglomerations may occur during precipitations. So, that is the disadvantage of two steps methods. So, now a technique to enhance the stability of the nanofluids that we have prepared by two steps method. So, what are the various various steps we can use by enhance the stability of the nanofluid? Chemical method and physical methods are there. In the chemical methods, we can use some surfactants to enhance the stability of the nanofluids that we have prepared. So, a specific surfactants we can use to stabilize that nanoparticles in that nanofluids, or by changing the pH of that fluids. So, by additions of acids or base we can change that pH, and based on that the stability of the nanomaterials in that fluids will enhance accordingly, or surface modifications of the nanomaterials that we can do in chemical treatments, and physical treatments, ultrasonications or homogenizations that we can do. So, by these two way we can enhance that stability of nanofluids that we prepared in a two step methods. Okay. So, in additions of surfactants, I said different type of surfactants is available. So, either cationic, anionic or amphoteric type non-polars or polars, means depending upon that base fluids we can choose that surfactants and we can add to prepare the nanofluids. Okay. So, here's hydrophobic nanoparticles. Suppose you have a metal oxide hydrophilic nanoparticles. So, they would be easily dispersed in polar base fluids like waters. Okay. If we have a CNT like, that is hydrophobic nanoparticles, so that would not disperse easily in that water. So, therefore, we have to use oils, that is non-polar type of fluids. So, when we prepare say CNT based nanofluids, so there we have to use non-polar fluids, that is good for stability we can enhance for that particular, and means CNT will disperse easily in oil type of non-polar fluids. Okay. And in case of the hydrophilics or metal oxides, then waters or polar based fluids we can use. Okay. Metal oxides and for that waters we can use as the base plates. Okay, so here different type of cationic, anionics, non-ionics, amphoteric surfactants are given, so that can be used for enhance the stability of that nanomaterials in nanoplates. Okay, so it has been observed that, so if we prepare single wall nanotubes waters nanofluids, if we prepare using HD based surfactants, it may stabilize for 3 months. So an HDS surfactants if you use for multiple CNT waters and nanoplates preparations, it would stabilize 90 days. So depending upon that surfactants and which particular nanoparticles or nanomaterials we are using to prepare the nanoplates, so that stability also depends on that. Okay, so pH also very important factor. So in that, this is if we change that pH of that solution, so nanofluid actually isoelectric points, when we discuss about the zeta potentials, we have said that, so if there is no net electric charges, means that is isoelectric point, so then the fluids would be unstable or coagulate tendency would be there. So therefore when we prepare a nano fluids, so then we have to maintain a pH. pH is very important, so to get a stable solutions. Okay, so in case of the copper water nanofluids, so we have to maintain pH 9.5, that is good for stability of that particular nanofluids. Alumina waters, copper waters, it has been observed that there is possibility for tendency for agglomerations. Okay, and there is possibility of sedimentations if it is pH is maintains below 7. So always you have to maintain above 7 pH. So here you can see copper water pH you have to maintain 7.6, and in case of alumina waters we have to maintain pH in between that. So then we can get a good stable solutions, fluids, stable nanofluids, so that we can prepare. And surface modifications by chemical treatments by using different acid treatments, so improve the CNT dispersions, or that would stabilize that CNT in the base plates. So here also physical treatments means chemical treatments by using surfactant, which already have discussed, and in physical treatments ultrasonications we can do, means we are adding nanoparticles in nanoplates, and after that if we do some ultrasonication, so stability you can see that will enhance. Okay, so even let us say if we want to prepare gold waters nanoparticles, so 10 to 60 minutes ultrasonications is good. So ultrasonications is important, 10 to 60 minutes, so we get a stable solutions. If we put excessive ultrasonication, that would reduce the size of agglomerated nanoparticles present in the nanofluid. Okay, so here's ultrasonications different steps, means their schematic diagram is showing, and so here depending upon the nanomaterials and different type of base fluids, so how long the sonication times I said that is important. So it may be means graphene ethylene glycols in that case, so 5 minutes to 10 minutes is okay. And when graphene oxide deionized water, so here 16 hours chargings and 1 hour sonications is good, and in that case HDS unstables to disperse in the graphenes and settles after 5 minutes. So homogenization, that is also very important physical treatments, so that is high pressures or shear force that would be applicable when we are preparing nanofluids that we can use. So nanofluid prepared with high pressure homogenizations that offers better dispersion and stability than those prepared by sonication. So after sonications we can also do homogenizations, or separately after mixing two nanoparticles and mix nanoparticles and base fluids so to prepare nanofluids, and after that if we do homogenizations. So here's actually CNT waters in HDS requires high pressures, that is means homogenization is requires, so that would gives a good stable solutions. Usually CNT don't if we use a CNT based nanofluids, then we don't use waters, that is use oils type of non-polar solvents we have to use to get a solutions nanofluids. But when water we are used, then HDS we can use as a surfactants, and in that case if we do homogenizations, then we can get a stable nanofluids solutions. Okay, so here, so what is homogenizer? So actually that is a homogenizer that actually consists of two micro channels that divide the feed streams into two parts, which are again combined in the mixing chambers. So, therefore, since we are dividing that fluids into two different streams, so therefore, a huge increase in velocity inside that mixing chamber that will be developed. So, as a result, a smaller diameter of the feed stream tubes resulting in high shears and large impact of the wall of the chamber and formation of strong cavitations within that nano fluids. So, here you can see in the high pressure homogenizer, here pressure fluids will come. So, it would be means pass through different channels. So, one is smaller, another is larger diameter channels is present, and as a result two different type of impact or shear force will forms, and that would help to mix that nanomaterials in that fluids, and we can get a stable solutions. Okay. So, here's pure waters, ethylene glycol, so both are mixed, base fluid formations is there, and multiple nanotube that was used as nanoparticles, mechanical mixings, mechanical star is there, then high pressure homogenizer use. This high pressure homogenizer setups is here, so you can see, and then so you can get multiple nanotubes, their base fluids is waters and ethylene glycols. Okay. So, here different type of surfactants and nanomaterials and base fluids that was used to prepare nanofluids. Here's ferrosulfuric oxides, metal oxides, ultrasonic precipitations, and 0.2 volume percent oleic acid was used, and 0.28% sodium dodecyl sulfonate surfactant that was used. So, to prepare ferrosulfuric oxides nanofluids, ferric oxide based nanofluids that was prepared. Similarly, multi-wall nanotubes that was prepared by CVD methods, and then 0.088% was used as a stabilizer or the surfactants. So, SDS multi-wall carbon nanotubes this is, and this is surfactants. So, how they are means interacted during that synthesis process. So, today is up to this. So, we have synthesized different type of nanofluids that is applicable for the heat transfer operations. So, how that using different type of nanomaterials, nanofluids we can prepare, and that can be applied for the heat transfer operations, and using nanomaterials that enhance that thermal conductivity of that fluids. Therefore, the overall heat transfer operations that will enhance rate of heat transfer. So, today is up to this. So, that is the applications of nanofluids or nanomaterials in heat transfer operations. Okay, so thank you.